evaluate the integral from 0 to 2 of 2x cubed minus 6x plus 3 over x squared plus 1 dx. Now this is different from the last problem because we are given limits of integration. So this is a definite integral, whereas the last one was an indefinite integral. Now what that means is we need to integrate this and then evaluate it at the limits of integration and take the difference. That is the fundamental theorem of calculus part 2. We should check quickly that it's continuous on this interval. The first two terms are a polynomial, so that's continuous everywhere. And this third one has a denominator that is always positive, so that's also always defined, and thus this is always continuous everywhere. We've got no issues, and so we can use the fundamental theorem of calculus part 2. And what we need first is the antiderivative, and that is what we did in the last video. So I am not going to go through those steps again. I'm just going to write it out. We got x to the 4th over 2 minus 3x squared plus 3 times the inverse tangent of x. And we don't need our constant because that's going to go away when we evaluate. And we need to evaluate this at 0 and 2. So let's evaluate it first at 2, and then we'll evaluate it at 0. So that's going to be 2 to the 4th over 2 minus 3 times 2 squared plus 3 times inverse tangent of 2. And then we can subtract from that 0 to the 4th over 2 minus 3 times 0 squared plus 3 times inverse tangent of 0. Now, as we evaluate these term by term, 2 to the 4th is 16, and 16 divided by 2 is 8. And then we have minus, well, 2 squared is 4, and 3 times 4 is 12. And then plus 3 times inverse tangent of 2. And I cannot think of a nice angle whose tangent is 2. So I'm going to leave that just like it is. And then on the right-hand side, we have minus. That first term is going to be 0. The second term is going to be 0. And that third term is 0 because inverse tangent of 0 is 0. So that whole thing is 0. So in the end, 8 minus 12 is negative 4. And so we have negative 4 plus 3 times inverse tangent of 2. We could certainly get a decimal approximation for that with that inverse tangent, but unless we're asked, it's generally best to give exact answers, and so I'm going to leave it just like that.